everyone, this is lecture number 34 E524 Digital MOS LSI Circuits, and today is November 10, 2020. There was a small correction in last lecture when I was saying that you need to like you can reduce the leakage by reducing VGS, reducing VDS, right, and reducing VBS also. So by mistake it was VDS I told has to be increased, but that's not correct. VDS has to be decreased, right, as it is logical also. Okay, so other than that, we talked about SRAM, we talked about the butterfly diagram, through which you can find out three important things, which is called hold margin, one is called read margin, and write margin. And using this, you know that what is the stability of your particular cell for writing, for holding, or for reading, right? So that's what we already studied, and we also know that hold margin are going to have two stable states, right? And for read, again, it's also two stable states. However, in the case of write margin, it's only one state because you are writing only one at a time, right? So there is not much variation here and there, right? So for that, we also studied like how to find out those margins from the butterfly diagram. So now moving to the next topic, which is called dynamic RAM. Or you can say that DRAM, that's the next class of memory. Notably, the memory organization at the top level will be same what we have done it for the case of SRAM, where there is row decoder and column decoder, and in between there are some cells are there where you are going to use word line and you are going to use bit and bit bar line, so that you can read, write, and hold the value which you want. However, in the case of dynamic RAM, this requires continuous refresh, and data is dynamically changing, right? Because you are going to use a capacitor to hold the value, right? So it's similar to what we were doing in the dynamic sequential circuits, where we were using a switch and a capacitor, where the capacitor was holding a value of the logic 1 or logic 0, and in between we were using some sort of transmission gate and other things, right? And we were not using the cross-coupled inverter. If you remember, like we haven't used that. However, it can also be used if you wish to have, but dynamic RAM is going to be use the capacitor to hold the values, right? So now let's go with the first step, that dynamic RAM, as I told you, it's going to store the value on a capacitor. So like we had SRAM, where you had word line, which is associated with the address, and the bit line, and actually bit bar was also there at the time, and Q and Q bar was there. So all these Q and Q bar was the state of the memory, states of the memories, and bit bar are used for read and write. This was the case for SRAM. In the case of DRAM, you do not have so many things. You are going to have only following things: word line and bit line. So whenever you're starting with the bit DRAM operation, similar to the case for SRAM, you also make the pre-charge of bit line. However, in this case, you are not pre-charged to VDD, you are going to pre-charge to VDD by 2. So this particular line is going to be pre-charged to VDD by 2. Let's keep this one in our mind. Along with that, if you look at the whole structure like this, I'm just showing you the structure for an example where there are lots of word line, lots of bit lines. So if you look at each one of the bit line, each one of them are going to have so many transistors, and because of that there will be some capacitor over here. So let's understand one more thing, that because of so many transistors, you are going to have one big capacitor over here whose name is CBIT. And the capacitor on which we are going to write or read the data, that's the C cell. As it has only one capacitor, and unlike the SRAM which had 6 transistor or maybe 8 or 10 or 12 transistor, for different purposes, we are going to have only one capacitor and one more transistor, this is going to act as a transistor which is going to make sure that it's going to write the value at particular address, right? So let's assume that when there is some data is written over here in C cell, right? And when this bit line is connected, so earlier bit line was not connected, let's assume that bit line was not connected, and C cell was already having some value, right? Let's call it Vx value. It was charged to Vx, right? And when I make this on, what is going to happen? It's going to make the charge sharing between two capacitors. One is C cell and one is CBIT. Notably, CBIT is also not a small number. You should match according to the speed requirement and what value you want to store it here. So storing the capacity and the current is going to drive the whole thing. If you look at this, you will understand that when this line was recharged to VDD by 2, and when you're connecting this capacitor, it's going to make such a way that the bit line will have two kinds of shift. Either it can go upside or maybe downside. Up and down are decided by the capacitor over here, CBIT, and capacitor over here, right? So there is a small change is going to be going up or going down. So it's not going with the full scale VDD value. It's going to have either some delta V upside or maybe delta V downside. So effectively it's a 2 delta V, and this delta V is depending on the fact that delta V is nothing but, if you look at this, if this is CBIT, when this is on, that delta V is equal to the VDD by 2 was already there with us, and this was charged with VDD by 2, and it's going to be divided with C cell divided by C cell plus CBIT as written over here, right? So It depends what value you have at C cell, whether it's going to take you plus side or maybe going to take you minus side. It's always division between these two capacitors, and accordingly you can program it to 1 or 0. Let's assume that it's plus delta V. If it is plus delta V, you need to understand that it's not only the structure which has row decoder and column decoder, but you are also going to have something called sense amplifier. So it's a part of maybe after 2 or 3 slides, that sense amplifier is going to sense this value whether it's plus side or at the minus side, and sense amplifier will give you the digital logic 1 or digital logic 0 at the output. So you need a sense amplifier. Now how does this sense amplifier look like? So if you remember, we already studied that previous topic, but for drawing that over here so that you can remember that what we have studied. So if you remember previously we studied this one, and here delta V is going to be fed. So if this delta V is positive, means this terminal is positive and this terminal is negative, then accordingly you will have digital logic 1 at the output, because it's acting as a comparator, and in this particular application we are going to call it as a sense amplifier. Note that it depends on your application whether you require this or not. If you are keeping this, it's acting as a resistor. If you don't keep it, it's acting as a latch, right? So this is what you can use it, right? And you can have the Q and Q bar. So here the most important role which is played by is actually the capacitor as well as the sense amplifier. Right? Looking at the overall structure, it looks like exactly what we had for the SRAM. Each one of the cell is kept over here. Each one of them is known as the cell, like we had SRAM. However, in this case, there is no bit bar line is required because it's becoming redundant. However, if you want, you can introduce it with a differential structure also. If you have a differential, then you can use that. Now let's understand that how you're going to use the sense amplifier to sense the output. So you can see here there are two sub arrays are there, one over here and one over here. Both are identical, and both have different, you can say that bit lines are already there. So these are the bit lines, right? And similarly, these are also the bit lines. So each bit line will have delta V and delta V. Notably, this is the open bit line structure which is acting as a differential one. right? So one side is plus delta V, then other side will be minus delta V. And in that case, because of this differential structure, the sense amplifier is going to give you the answer depending on which side is higher, right? So if this is plus delta V and if this is minus delta V, whichever is higher, right? If plus delta V is higher at the plus terminal, then the output is logic 1, and minus delta V is higher than plus delta V other side, so then it's logic 0, right? So this is how this is decided. For the case of differential line, if you don't do that, but there is something called the folded bit lines, because there is already in this particular structure we have availability of cells uh, like beside each other. So one cell is there next to the other cell. So in that case, there are many cells are there. So what I'm doing, like if one cell is available where there is already a connection, let's assume that this is a connection, and I want to read or write over here. So whatever the cell is here, it's going to be read. While doing this, look that here other sides are not going to be programmed, right? So here you are reading, but other sides are not reading it. So other particular line will have a lower value than what you are programming, right? So in that case, you're going to have difference of delta, and whichever is higher, you know that look, if you are connecting this way and if you are looking at this line, then the output is logic 0 or logic 1 with respect to the minus line. So folded bit lines has advantage that you're going to have sense amplifier from the same structure. You don't need the differential, and it's advantages in terms of if you draw the layout is also kind of way that you can have the layout which is actually packed one, and it's a square, and you can design as you want, right? So like unit cell is shown over here. So this square box is a unit cell, and you can program it and you can see the output at the output of the sense amplifier. Okay, and of course you need word line decoder and the other side of column decoder, right? Okay, it is also popular that you don't use only and only 1T DRAM. There was 1T DRAM because it has one transistor and one capacitor. So this was the structure. Here the problem is actually the delta V which you are seeing is very low value. So you need very powerful sense amplifier which can sense so much small value, and accordingly you have to design a W by L. Notably, for a given frequency you need to increase W by L so that it can give you lower resistance and the lower propagation delay, and your output is settled within the time. But this delta V will be smaller over here. But if there is a line where you have word line and WBL and RBL, one is write bit line and one is read bit line. So when you are writing with making this on, let's say whatever you want to make it on. So when you are writing it, you can write that on this capacitor, logic 1 or logic 0, right? So if this side, if it is logic 1, the other side will be logic 0, right? Because it makes the connection here. Similar to that, if you write this to logic 0, as this is open, it's connected to the place where it was. So it latches the previous value. Notably, I am not drawing it, but here at this node, there is a parasitic capacitor associated with this transistor and the overlap capacitors of this transistor and all the total capacitors which are reflected over here. That has to be seen. And for this RBL line, there is another capacitor. By the way, we are calling this one as C bit capacitor and this one as C cell capacitor. Notably, there are capacitors also here. Right now, I am not taking into account for the analysis of the DRAM where this particular node value of that's going to be divided with VDD by 2 times C cell by C cell plus C bit. Notably, when it's logic 1, the transmission of logic 0 is seen. So here, more stronger signal is possible, or I would say that bigger delta V is possible compared to this one. And that's how, like, you need even if your sense amplifier is little bit weak, that's going to work without having any problem. So this was one of the technique which has actually 3 transistors. That's why it's called 3T DRAM. You need to analyze such a way that which particular node is important for you, and accordingly you need to find out the value of the W by N. You can think about, like, when there are 2 excess transistors A1 and A2 and there is a transistor over here. So you need to find out that for a given driver transistor, which one has to be more or which one has to be low. Note that all 3 transistors right now here are all NMOS. So there is no usage of PMOS over here. So accordingly, you can see, talking about the second technique where you can read and write separately. So this is write word line and this is read word line. When you want to write down something in this cell, so here the DRAM capacitor is this transistor where you are writing or reading from this transistor. So when you are writing it, you have to make sure that WWL has to be on so that it makes the connection over here. And depending on what value of the right value is here, that is going to be written over here, either logic 1 or 0. If the value is 1, the output is 0 and you can write down here logic 0 without having much difficulty, right? As you know that which value of transistor has to be higher, right? And if the value is not 1, but if it is 0, this particular transistor is going to be off and this particular node stay at the value where it was. So previously stored value, right? And whenever you want to read this one, I need to use this read transistor with read word line signal. So when I'm doing this, I can have the output as logic 1 or 0. Third technique, which is similar to what we have seen in a case of SRAM, but it does not have PMOS because PMOS is not required. It's a redundant thing. But if you want to use it, you can use it. There is no problem, right? That is also one of the advantages thing. But when you are using it, it's increasing not only 2 transistors in a cell, but as many cells you have, it will be multiplied by 2, right? So area wise, it's taking more area. So if it is not required, then it's okay, fine. Because look, even if it's not reaching the required value of logic 0 or logic 1, the thing is it's going to be taken care by the sense amplifier. So sense amplifier is going to sense the value of delta V at the positive side or the negative side, and it will give the output. So here, if you look at this, It's similar to what we have studied. And here you also have the Q and Q bar, right? Or Q underscore B. And two excess transistors are there, A1 and A2, and maybe two driver transistors, D1 and D2. So here there are two transistors on which you are writing or reading the value. So here the effective capacitance is playing the role. Good part over here is one side is 1, then other side is 0, right? So that will have the positive regeneration, and because of this positive regenerative nature, it makes sure that you can have the better output in terms of the delta V. So delta V will be the strongest over here in the 4D DRAM structure, right? So this was like very easy, and it's whatever we have studied for SRAM, it's valid for DRAM also, and you are going to have row decoder, column decoder, sense amplifier. And sometimes you don't need column decoder also. So accordingly, you can design it. You fix your target for the SRAM and DRAM, and start doing your project work, right? So this is also the end of the DRAM. DRAM does not have many things. DRAM has only a few things which you need to understand, that it's going to store the value on a capacitor. Now let's move to the next part, which is called read-only memory, or the ROM. Where the difference between read and RAM is that, like, this read-only memory, you can only read the memory, right? And when like even if your power is down, the data remains staying there. It does not get destroyed. And you can see that this is one of the easiest ROM which has been designed over here, where it requires 2 to 4 decoder, and this is designed for the case that the way the structure has been made, it's known as NOR ROM. You can see over here that over the, first of all, word wise, there are 4 words are there: word 0, word 1, word 2, and word 3. These are associated with the addresses. You can see that address word 0, if you look at just word 0 over here, so I can see that it's associated with 0 1 0 1 0 1, right? 0 1 0 1 0 1, right? So that is the word which is available over here, because these are the transistors shorting with that. Looking at word 1, it's 0 1 1 0 0 1. If you're looking at the word 2, it's 1 0 0 1 0 1. And for the word 3, it's going to be 1 0 1 0 1 0, right? And at this particular address, you are writing what you want to write, whether it's the logic 1 or 0. And when you are seeing this, you can see that when you are looking at the output, look, there are various outputs are there, Y0 to Y5, right? So if you are looking at just one output at a time, like Y5, in the case of Y5, it's actually makes the connection with the transistors which are connected to the ground, right? So you can see here that this is the thing which is connected over here, right? Similarly here, so you can see each one of the line has transistors in parallel, so it makes the connection something like this. let's say I'm talking about some y2 or y3, whatever it is, and here gate is connected with the word line or the word whatever is given to you, and this side it's connected to ground. So this look like a pseudo NMOS structure which we have studied in combinational circuits, right? It's a pseudo NMOS structure where this PMOS as a load and the gate is connected to always ground. So it's same as like pseudo NMOS pull-up network. And you can see here, if you look at the structure, this combinational logic is going to implement, if this is, let's say, W0, W1, and so on, it's going to make W0 or W1 or and not of that. So that's going to make the NOR function. And that's why the name of this structure is NOR ROM, right? And it follows exactly the way it's following the pseudo NMOS pull-up. Note that there is extra word is added over here. It's a weak pseudo NMOS pull-ups. We are keeping weak pseudo NMOS pull-ups because if it is not weak and if it is strong means WIL is quite high compared to the rest of the NMOS transistors, then it's going to make connection with VDD always, right? And there are very likely that you're going to make the connection with 0. So logic 0 cannot be achieved efficiently, right? And I'm saying efficiently means logic 0 as 0 volt. Even if it's in micro or millivolt, it's okay, fine, like 1 or 2 millivolt. But if it is going in 200 or 300 millivolt in 1.2 volt technology, it's a quite big thing, right? So if it is touching the noise margin high or low, then touching the noise margin low, then of course it creates a problem for you. So in that case, it's better to avoid it with taking the weak pseudo NMOS pull-ups, right? So this theory is already known to us, and we already studied while understanding the combinational logic, right? And this was also the question in quiz 1, that what value or what problem will be associated with pseudo NMOS network, right? Okay. This is known as the dot diagram drawn from the same circuit which has been given over here. So because of this connection, which is in horizontal and and in vertical, so it's exactly from here. So all these lines which are vertical, same vertical lines has been drawn in the dot diagram, and all the lines associated with the word are also going to be drawn, and it is creating such kind of one kind of matrix. Here, wherever you see a transistor which is connected to ground, it needs to be giving you dot. So wherever there is a transistor, you are going to keep the dot. So same diagram has been drawn over here, which gives you the information that where the transistors are. Actually, this is very popular and very useful technique, which has been in the later case, it has become used in programmable logic array, where these connections are made with some required fuse and or the switches, which are like MOSFET switches, through which you program that particular node on and off, and you are going to have this required sum of product. So in the case of PLA, you are going to have the sum product. So later stage we are going to study that also, right, before signing off for the memory. So I believe there should not be much problem in this, but there is another one is now the name has been changed, NAND. Okay. It's like name itself reveal that in the case of NOR, all the transistors are in parallel. So here all the transistors were in parallel, so that you are making the NOR RAM, and in this case, when the transistors are in actually series, you are making something called NAND, because the output which you are going to take from here, it's going to end of many transistors, right? Or you can, if you want to write down here, it's word 0 or end word 1, end of this one. So it's a NAND operation, right? So this is a NAND operation. The only problem here is, like, there are so many transistors in actually series, so it's quite difficult sometimes to get enough voltage across a transistor, right? And it's sometimes difficult also, but the good part of this one is it's actually having the lesser area compared to the NOR, and that's why, like, most of the time people are making the NAND memory rather than the NOR memory, because all associated with memory is actually the cost of area. You want to see the smaller and smaller memory stick, right? You don't want the bigger one. So same pseudo NMOS network will be here. Right? And they have to be weak, as we know that. Why? Right? And there are so many transistors which are connected in series. Right? So this is a very simple thing, and accordingly you can find out its dot diagram also if you wish to find out. So wherever the transistor is, you are going to make the dot. That will tell you that where the transistor is, and it's going to be on or off, right? Okay. So the after understanding all these things, it's taking you the different level of things, but the next level which I'm going to teach, it requires understanding of device physics and all. However, we are not going to touch the device physics in detail. I'm just going to tell you how it works and all. But I believe that you know about MOSFET, which looks like as follows. So this was the standard thing which we are using till now. But and MOSFETs have its technology shrinking through the Moore's law, right? And also voltage is also scaled down. Now, in the case of maybe 28 nanometer, it's around 1 volt, right? And it can go below that also, right? Which is the desirable thing for MOSFET. However, there is one more class of memory, which is non-volatile memory, where we need not this kind of transistor, but I need other kind of transistor whose name is floating gate transistor. Which look like this one. Right? Instead of having just one metal contact or the one control gate, you're going to have actually one more polysilicon floating gate, which is between two silicon dioxides, right? There are many other variants are also available for this. Like one of them is also like this also is available. Instead of this, there is one floating gate here also available. So it depending on the technology. Like this is from Tower Z, where there are some extra side wall gates are available. Here there are floating gates which are in between available. And because of that, now new symbol I'm going to introduce to you, which is going to have three lines over here. But this is might be source or drain, and this might be drain or source. As you know, like depending on the voltage, you can change it. And this is gate, and what we are connecting here, it's a floating gate. Whereas, because of the side wall, you might have this kind of symbol is also, this is popularly used in S flash or super flash memories. We are going to use such kind of transistor. For floating gate, we are going to use it for NVM flash memories. Right now, we are not going into the detail how it works, because that will be the next understanding of the memory, right? So here just one structure has been kept just for your information, that NAND flash memory, as the name suggests, all the transistors are in series, but there is nothing like, you can say that there is nothing pull-up network, nothing like pull-up, right? So there is no pseudo NMOS pull-up.